Right, so hopefully you can all see that. Sometimes I get it wrong, I know. I'm sure you'll yell if you can't. So I've got a list of people in front of me. So if you do want to interrupt me, feel free. Just raise your hand and I should get a notification. Right, so as I just said, we're going to talk about virtual machines, containers. We've got a couple of videos from IBM, which I hope be interesting. What I think we'll do is we'll talk about virtual machines first. We'll see if there's any points to discuss at that point, and then we'll talk about containers. And then towards the end, see if there's any further discussions or chats or points to raise. All this. Right. So this is the agenda for the day. Start off with the problem of what's called bare metal servers. Talk about virtual machines, containers, orchestration, translations, and also uses on the desktop. So this is the whole reason why we've got virtual machines or containers. If you imagine you've got a bare metal server, in other words, you've gone and bought a physical computer, you bought it home and you've put the CDs in and you installed your operating system and installed your applications. It's a physical bare metal server, something you can trip over. But this has quite a severe problem. So let's say we've got a small business and they are in the business of AI. And this business has to do multiple functions. They have to do their software development work. They've got to use, got to train their large language models. That's going to use lots of compute resources, but they also need to run payroll, and the payroll has to run once a month. So the way you'd normally do this is you get a first server and you install it, get the CDs, install the operating system, install the payroll application, and off you go. And then the software development team would have a second server or several servers, and they would do exactly the same thing. They would get their own hardware, they would install their operating system, and they would do their whatever they're doing, this large language model training or whatever the development team in the basement is going to do. Now, the issue with this is, of course, you probably already know, the payroll application is going to be very infrequently used, once a month. So server 1 is going to remain idle, while server 2 is going to be running 100% most of the time. So this is a very poor use of resources. We've got basically one idle server and one server at full capacity. So you could put both these applications on a bigger server, but problem with that usually is these two applications might need different operating systems. You need to be careful that the payroll doesn't run too slowly when the development teams are hammering out what they're ever doing in the basement. And above all, you need to be very careful on security. If you've got a bunch of developers in the basement and they find you're running payroll system on their server, they're going to get paid pretty well at the end of the month. You can assume their payroll server is going to have a few zeros at the end of it. So enter virtual machines. So the whole purpose, this is designed to fix a problem that we talked about. You buy hardware, and if you have one application per server, it becomes very inefficient in terms of resources. So instead, what you want to do really is to buy perhaps a bigger server and use it for all the applications you need, but also manage all the resources, CPU, memory, and such like. So the way these things work is you have hardware as normal, CPUs, memory, and disks, and so on. You usually have an operating system, and now we install a virtual machine monitor or hypervisor, depending on who you talk to. Now, this bit of software allows you to run virtual machines. Now, these machines, it's quite important to understand this. These machines, the virtual machine monitor or hypervisor, emulates hardware. So it presents to each of these virtual machines a view of the hardware. So you could grant 2 CPUs to virtual machine 1 and 4 CPUs to virtual machine 2. You could grant memory, different amounts of memory and such like. Now, these virtual machines are full machines. In other words, they need an operating system installed. So you've got an operating system installed on this virtual machine, an operating system installed on this virtual machine, and then finally you can install your applications. So virtual machines are really about running operating systems. And once you've got the operating system running, then you can install your application. And the reason to do this, as I said before, is to make better use of your hardware resources. And this is what virtual machines are about. So what I'd like to do now is to emphasize this with a video from IBM, and then perhaps after that, we'll pause to see if there's any discussions.
Hi, my name is Kaylee Bovey with the IBM Cloud team, and today we're going to be talking about virtualization. As you know, virtualization is a fairly old technology, but it's still super relevant to building your cloud computing strategy today. So first off, what is virtualization? Simply put, virtualization is the process of creating a software-based or virtual version of something, whether that be compute, storage, networking, servers, or applications. And what makes virtualization feasible is something called the hypervisor. So we're going to write that here. And what a hypervisor is it's simply a piece of software that runs above the physical server or host. And there are a couple different types of hypervisors out there. And what they do is essentially pull the resources from the physical server and allocate them to your virtual environments. There are 2 main types of hypervisors out there, one being type 1, very simple to remember, and 2, you guessed it, type 2. So let's start with type 1. A type 1 hypervisor is a hypervisor that is installed directly on top of the physical server. They're also called bare metal hypervisors. So we'll write that up here, just so you can remember. These are the most frequently typed of used hypervisors, and they're most secure, they lower the latency, and these are the ones that you'll see in the market the most. Some examples would be VMware ESXi, or Microsoft Hyper-V, or even open source KVM. The other type of hypervisor is a type 2 hypervisor over here. And what makes these different is that there is a layer of host OS that sits between the physical server and the hypervisor. So, by that nature, they are also called hosted. These are a lot less frequent. They're mostly used for end user virtualization, and you might see some in the market that are called like Oracle VirtualBox or VMware Workstation. Again, they're a lot less frequent. They're a bit more, they have a higher latency than a type 1 hypervisor. So once you have your hypervisor installed, you can build virtual environments or virtual machines, or simply put, VMs. So let's spin up some environments. So what makes a VM a VM? A VM is simply a software-based computer. They run like a physical computer. They have an operating system and applications, and they're completely independent of one another, but you can run multiple of them on a hypervisor. And the hypervisor manages the resources that are allocated to these virtual environments from the physical server. So because they're independent, you can run different operating systems on different virtual machines. So you could run Windows here, or Linux here, or Unix here, for example. And because they're independent, they're also extremely portable. You can move a virtual machine from one hypervisor to another hypervisor on a completely different machine almost instantaneously, which gives you a lot of flexibility and a lot of portability within your environment. So looking at all of this, this is the core of virtualization as a process. So let's talk about a couple key benefits that you want to take away from this. One, cost savings. When you think about this and the fact that you can run multiple virtual environments from one piece of infrastructure means that you can drastically reduce your physical infrastructure footprint. This is consolidation at its core, and the fact that you don't have to maintain nearly as many servers run as much electricity, save on maintenance costs, means that you save on your bottom line at the end of the day. Number 2 would be agility and speed. So like I said, spinning up a virtual machine is relatively easy and quick. A lot more simple than provisioning an entire new environment for your developers if they say they want to spin up a new environment so that they can run a dev test scenario, whatever it might be. Virtualization makes that process a lot simpler and quicker. And 3, lowers your downtime. So let's say that this host goes out unexpectedly. The fact that you can move virtual machines from one hypervisor to another on a different physical server means that you have a great backup plan in place, right? So if this host goes down, you can simply move your VMs very quickly to another hypervisor on a machine that is working. So with this is really virtualization today. And like I said at the beginning, virtualization is a technology that's a few decades old at this point, but it's still super critical to understand for your cloud computing strategy today. Thanks for watching as we discuss the basics of virtualizing.
Right, I'll sum up and then I'll open to see if there's any discussion points on virtual machines. So just to summarize, so the hypervisor prevents emulated hardware to each virtual machine. The disk image for each virtual machine is created when you install the operating system. You have this big file on the file system, which represents the hard disk. It can be cloud hosted, a server on the internet somewhere, or, on your local premise. And popular vendors, you've got Azure, AWS, and so on and so forth. One issue that I've seen, there's only a few standards between different vendors. So, if you've got Azure virtual machine, trying to move it to VirtualBox is quite tricky. Now, what you tend to do on these operating systems inside the virtual machines is you can add additional tools in there to help improve performance. They're called guest tools. And allocate hardware resources, CPUs, memory, and such like, and you can vary them dynamically. So in the payroll example we're talking about, you could allocate almost the whole server to the development team for most of the month, and then chop it down a bit to something actually quite small so that payroll can run once a month. Important applications are isolated for security, but they are slow to start up, and I will demonstrate this and you'll see the difference. And of course, the full guest operating systems mean there's overhead disks and CPU and such like. And a good point here is that not all hardware can be supported because you need this emulation layer. If you've got some weird GPU, latest version on your physical server, if the hypervisor doesn't support it, then you won't be able to use it in your virtual machine. And, it requires the same CPU type as the physical host is. So if your physical server has got Intel CPUs in it, then your virtual machine guests will also have to be Intel. Right, so I see a question there, Paul.
Yeah, I was just wondering about this separation. There's two cases. You can either have instances of hypervisors running all at the same time concurrently, although some of them might be just idling, or you can you can load up a hypervisor when you need it, and then presumably you overwrite the RAM and everything and trash it afterwards. But in each case, you have to enforce, and I'm not quite sure how it's done, security between the different virtual machines, and particularly in the case of errors and crash outs and things like that, and the cache and the video RAM, things like that. So how is that managed?
Yeah, so the hypervisor manages all this for you. So you mentioned crashes. So if your operating system crashes, then the virtual machine will just stop running. There is no, unless there's horrendous bugs in the hypervisor, there is no way for one virtual machine to overlap or overspill into another virtual machine. They really are completely separated. So what you have to do, if you want these two virtual machines to talk to each other, you have to go to an extra step and enable networking between them in some way. And
Right, but you're also sharing the hard drive and for permanence and the RAM. And are you saying that the hypervisor is trusted to manage all that too?
yes, it has to be trusted to do that. So the hard disk, there is a physical hard disk on the machine, but then each virtual machines just sees their own version of that disk. So what you do, you create this big file on the underlying hard disk, which is a binary blob, a disk image, and then you present that to the virtual machine. So the virtual machine can read and write into that single file on the disk, but can't write to anywhere else on the disk.
Right. Okay. Yeah.
So
okay.
you're right. Security is a concern, right? And you have to
Yeah.
trust your hypervisor that it's bug-free in this regard.
So if I'm running, say, 10 different virtual machines, I'm running effectively, I'm sort of installing 10 different or potentially 10 instances of the same operating system, whether that be Windows or Linux or whatever, on the box. Does the hypervisor kind of manage it as to how much of that it needs to install, or do you end up needing a lot more memory and a lot more resources to run this system rather than having two separate boxes?
Now,
You see where I'm coming from?
Each virtual machine is completely isolated. So each virtual machine has its own running copy of the operating system. So if you've got 10 virtual machines with 10 instances of the same version of Windows, you've got 10 copies of Windows. So you have to install it 10 times. Now, in practice, if you do these things commercially, there are tools available that will take a CD from Windows or a disk image and automatically install the operating system for you. So it's in practice, you don't have to go through all the menus, the installation menus. But yes, each virtual machine has its own copy of the operating system. It is not shared between virtual machines.
Okay. And does that mean when there's a large update comes out, whether that's for security or functionality, you end up having to roll that across all of those virtual machines as well?
Yes.
Yeah. Okay. So I'm guessing that although you're using probably a lot less physical resources to do this, you can end up needing quite a significant amount of working memory to be able to run them efficiently.
Yes, and bear that in mind. We've got a second video to watch about containers, and that exact point will come out there. But of course, the advantage of virtual machines is you can run Windows 11 on one virtual machine. You can run Linux, you can run Mac OS, you can run some version of Unix, you can run BSD. Whatever operating system you like, really, will work. Peter.
Thanks for it. That's really good. I just like to understand the nitty gritty. The version, because you say you're emulating the hardware, so somewhere in Windows or whatever operating system you've got, Unix, there's a call to the hardware. So somehow that particular instruction has to be trapped out in some way. How does that work?
Yeah, good question. So what actually happens is these virtual machines have standard, usually quite old hardware emulated. So the network cards, for example, and one of the first network cards was a card from Novell called the NE2K. And that's a very basic network card, very simple network card, and actually quite easy to emulate. And so these virtual machines have emulated this hardware in software. So when the operating system wants to send a packet out to the network, it calls to the virtual machine saying, I want to send a packet. And then the virtual machine will take that, translate it down to its real network and send it over the network. So yes, so each operating system call goes through this emulated hardware layer.
That's very interesting, very interesting. So as far as the application programming interface, that is whatever the host operating system offers. So that's one layer in the system, isn't it? Yeah.
Well, virtual machines just need to offer emulated hardware.
hardware.
Virtual machines don't care too much about APIs and such like. They just need to present a hardware.
Okay.
The exceptions to that is various things like booting and BIOSes and stuff like that. And there's, a little bit of fudging going on in that area. But basically, virtual machines are really about emulating hardware.
So if you've got a funny device, as you said earlier on, we're talking about being able to emulate disks, maybe tapes, maybe CPUs, memory, networking cards. There's kind of a range of standard bits of hardware it would emulate. But if you want to do something funny, you've got to. It's much harder for the virtual machine to emulate that hardware, is what you're saying.
Yeah, that's generally correct. I mean, recent virtual machines will handle USB quite well now. So some of these weird devices, I don't know if you're doing, software-defined radio. I'm looking at David's screen here. If you're doing software-defined radio, you've got a USB device. That will now probably work in a virtual machine simply because USB is supported.
So
that's
USB
how I
is
run
supported.
my SDM
Yeah.
off of a VM.
Yeah.
One comment can I make is that what you talked mostly about the Type 1 VM, so specific to Linux is KVM, and that is different in that your VMs don't run on the bare metal. With KVM, it's functionality in the Linux kernel itself. So you would install a kernel, say you install Ubuntu on your machine, and you could use it with the Ubuntu desktop, but it includes the VM functions inside. So you could run VM Manager, and it will then run VMs on top of, in effect, on top of that kernel. So it's like a shared kernel. The advantage of that is that that kernel is already able to operate on your hardware.
Yes.
Okay? The disadvantage is that it only runs on Linux. You can't use it in Windows, but you could run a Windows VM with it.
Yep. No, that's a good point. I mean, IBM class that as a Type 1 because there's no separate or additional operating system terminology, I guess. And right, I've got one more slide on virtual machines, but since we paused for chat, any other comments for virtual machines? But I do have one more slide.
What's the licensing position, Peter, on this sort of stuff? Because obviously, if you run Windows on top of this, how's the licensing work commercially?
Read the agreement. So I'll give you an example that I happen to know about.
Yeah.
So I've got a Mac. I'm using a Mac now in front of me. And when I buy a Mac, I've got a license to use Mac OS. And if you read the license agreement, it also gives me the license to run 2 virtual machines.
Okay.
And if you buy an operating system, I suppose that's one novel thing. If you buy an operating system, you just simply have to check the license agreement. These days, mostly you'll have a separate license agreement for a virtual operating system, which is somehow cheaper. And if you use the cloud services such as Azure or Google Cloud, they will take care of the license agreement for you.
Thank you.
All right. Any other questions before we push on? Find my share again. All right, so when you're setting up a virtual machine, there's obviously a few things you need to configure. The disk sizes and speeds and such like. So you could actually have an additional hard disk plug into your host, and you give that hard disk wholly over to your virtual machine, so nothing else can access it. Or more commonly, you create a disk image on your machine of a particular format. So a few configurations and whatever is on your disk initially. How many CPUs to grant to your virtual machine, type and speed and cores and such like. And mostly really is memory. How much RAM do you want to allocate to your virtual machine? And this is example configuration on Azure. So you can go to Azure. It's a cloud virtual machine, and it gives you all these settings. When you create your virtual machine, you have to give a name, where physically is installed. And what what Azure and the other cloud providers do, they can actually give you a starter image. So instead of inserting all the CDs, they'll have maybe 10 preset images that can start off your virtual machine to get going. And then, how many virtual CPUs and memory and such like. And of course, because this is a paid service, the more virtual CPUs and more memory you want in your virtual machine, the more it's going to cost you. And so on. So this is virtual machines. Any other questions before we move on to containers? Nope. Okay, so containers. The reason I've done this talk really is because virtual machine and containers are often mixed up. So I thought if we have a talk about both of them, and then we can compare. So this is containers view of life, similar to what we had before. So we've got a big physical server, we've got our hardware, and we've got our operating system. Containers work differently. So in containers, you'll have a very lightweight container engine. It really is kind of quite tiny. And then what you do is you run containers rather than virtual machines. So terminology here, a container is a running instance of your application. So here we're running 2 containers. And one thing you'll notice here, what's missing is inside the container is no operating system. This is a key difference. Containers are about running applications. Virtual machines are really about running operating systems. So what you have inside your container is really only your application plus any libraries or binaries that application might depend on. So containers are more lightweight than virtual machines because there is no containers. But all the same, you can use containers to run your payroll application. You can use containers to run your large language model training by the dev team. So as before, let's have our little talk from IBM to drill into this in a little bit more detail.
Hi, everyone. My name is Sai Venom, and I'm a developer advocate with IBM. Today, I want to talk about containerization. Whenever I mention containers, most people tend to default to something like Docker or even Kubernetes these days. But container technology has actually been around for quite some time. It's actually back in 2008 that the Linux kernel introduced C groups or control groups that basically paved the way for all of the different container technologies we see today. So that includes Docker, but also things like Cloud Foundry, as well as Rocket and other container runtimes out there. Let's get started with an example, and we'll say that I'm a developer and I've created a Node.js application, and I want to push it into production. We'll take 2 different form factors to kind of explain the advantages of containerization. So let's say that first we'll talk about VMs, and then we'll talk about containers. So first things first, let's introduce some of the things that we've got here. So we've got the hardware itself, just a big box. We've got the guest, or rather the host operating system, as well as the hypervisor. The hypervisor is actually what allows us to spin up VMs. Already, let's take a look at this shared pool of resources with the host OS and the hypervisor. We can assume that some of these resources have already been consumed. Next, let's go ahead and take this JS application and push it in. And to do that, I need a Linux VM. So let's go ahead and sketch out that Linux VM. And in this VM, there's a few things to note here. So we've got another operating system in addition to the host OS. It's going to be the guest OS, as well as some binaries and libraries. So that's one of the things about Linux VMs, that even though we're working with a really lightweight application, to create that Linux VM, we have to put that guest OS in there and a set of binaries and libraries. And so that really bloats it out. In fact, I think the smallest Node.js VM that I've seen out there is 400 plus megabytes, whereas the Node.js runtime and app itself would be under 15. So we've got that. We go ahead and let's push that JS application into it. And just by doing that alone, we're going to consume a set of resources. Next, let's think about scaling this out, right? So we'll create 2 additional copies of it. And you'll notice that even though it's the exact same application, we have to use and deploy that separate guest OS and libraries every time. And so we'll do that 3 times. And by doing that, essentially we can assume that for this particular hardware, we've consumed all of the resources. And there's another thing that I haven't mentioned here, but this JS application, I developed it on my MacBook. So when I pushed it into production to get it going on the VM, I noticed that there were some issues and incompatibilities. This is the kind of foundation of this big he said, she said issue where things might be working on your local machine and work great, but when you try to push it into production, things start to break. And this really gets in the way of doing agile DevOps and continuous integration and delivery. That's solved when you use something like containers. It's a 3-step process when kind of doing anything container related and pushing or creating containers. And it almost always starts with first some sort of a manifest. So something that describes the container itself. So in the Docker world, this would be something like a Docker file. In Cloud Foundry, this would be a manifest YAML. Next, what you'll do is create the actual image itself. So for the image, if you're working with something like Docker, that could be something, there'll be a Docker image. If you're working with Rocket, it would be an ACI or application container image. So regardless of the different containerization technologies, this process stays the same. And the last thing you end up with is an actual container itself, that contains all of the runtimes and libraries and binaries needed to run an application. That application runs on a very similar setup to the VMs, but what we've got on this side is, again, a host operating system. But the difference here, instead of a hypervisor, we're going to have something like a runtime engine. So if you're using Docker, this would be the Docker engine. And different containerization technologies would have a different engine. Regardless, it's something that runs those containers. Again, we've got this shared pool of resources, so we can assume that that alone consumes some set of resources. Next, let's think about actually containerizing this technology. So we talked about the 3-step process. We create some, a Docker file, we build out the image, we push it to a registry, and we have our container, and we can start pushing this out as containers. The great thing is these are going to be much more lightweight. So deploying out multiple containers, since you don't have to worry about a guest OS this time, you really just have the libraries as well as the application itself. So we've scaled that out 3 times. And because we don't have to duplicate all of those operating system dependencies and create bloated VMs, we actually will use less resources. So choose a different color here and scaling that out 3 times. We still have a good amount of resources left. Next, let's say that my coworker decides, hey, for this JS application, let's take advantage of a third-party, let's say a cognitive API to do something like image recognition. So, let's say that we've got our third-party service, and we want to access that using maybe a Python application. So he's created that service that accesses that third-party APIs, and with our Node.js application, we want to access that Python app to then access that service. If we wanted to do this in VMs, I'm really tempted to basically create a VM out of both the JS application and the Python application, because essentially that would allow me to continue to use the VMs that I have. But that's not truly cloud native, right? Because if I wanted to scale out the JS but not the Python app, I wouldn't be able to if they were running in the same VM. So to do it in a truly cloud native way, essentially I would have to free up some of these resources, basically get rid of one of these VMs, and then deploy the Python application in it instead. That's not ideal. But with the container-based approach, what we can do is simply say, since we're modulars, we can say, okay, just deploy 1 copy of the Python application. So we'll go ahead and do that. There's a different color here. And that consumes a little bit more resources. And then, with those remaining resources, the great thing about container technology, that actually becomes shared between all the processes running. In fact, another advantage, if these container processes aren't actually utilizing the CPU or memory, all of those shared resources become accessible for the other containers running within that hardware. So with container-based technology, we can truly take advantage of cloud-native based architectures. So we talked about things like portability of the containers, talked about how it's easier to scale them out. And then overall, with this kind of three-step process and the way we push containers, it allows for more agile DevOps and continuous integration and delivery. Hey. Hi, everyone. My name is Sai Venom.
Got away with it. Okay, so hopefully that's a fairly good description of containers versus virtual machines. And we touched on the point that Paul was making about resources. So here's some terminology there. So container is the running entity. And containers, when you start them up, you have to have a container image. So container image is something that you start a container from. And if you've got a container image, you can start 10 containers up from that same image. Interesting aside here that container images consist of layers. And when you run the container, you see like the summation of all these layers. So if you're building a container image, you might start off with a set of libraries from Linux. And then layer 2 might be a web server, and layer 3 might be your particular web server configuration. And these 3 layers will be combined into a single container image. And when you start the container will see all 3 of those layers at the same time. You know, there's an additive effect there. So as we talked about, containers are lightweight. There's no operating system, which is the big difference here. And the whole point of containers is to run a single binary. So that single binary might be your web server, it might be your database server, or it could be your, software-defined radio application or something. So you start up a container and you give it a binary to run. And when that binary is finished, by the way, the container stops. So container lifecycle are tied into the lifecycle of your application. And of course, multiple containers may be networked together. What it's really about is access control. It's about security between running containers. You know, sometimes you want to create an application that consists of several parts. You might have a web server and a database, and you might run these in 2 separate containers and then network them together. It can be cloud hosted or on-premise, of course. And popular vendors include Docker, Builder, Podman, Containerd, and so on and so forth. One interesting aspect here on containers is there is a standards body called the Open Container Initiative. And they determine the standards associated with both container images and container runtimes, which means you can really take a container image created from one tool and use it on a completely different tool. They are interchangeable, and that's not always true with virtual machines. And also the Open Container Initiative defines how these containers are run, as well as how the images are created. So this is very much a standards-oriented system. And of course, you want to allocate resources, the same as you do with virtual machines. And applications running inside containers are by definition isolated. And these applications now are very fast to start because you're not waiting for an operating system to start. A big point here is you're always using the same CPU type and operating system type as a host. So if your host is Linux, you can run Linux containers, or at least Linux applications. If your host is Windows, you can run Windows containers. You can't run a Windows container on Linux. So like virtual machines, there's a few key configurations. I will go through this fairly quickly. Container images are often downloaded from a container registry. Places like Docker Hub have got hundreds of thousands of container images that you can download. And if you can think of any common application, it will be there to download and run. And the format of these images is server, an image, and a tag. So it's normally Docker Hub / Oracle database : version 1. So you do have to specify, or you can specify or limit rather, CPUs and memories and networking. And this is the container configuration for Azure, just so we can compare it with a virtual machine. So here you'll see that we've got the link to the container image here, which is a Linux image, and we see the host name, a parent directory, a name of the image, and the : latest is short form for the latest. But very often you can put : version 1, version 2 if you want to go back to an older version. And the sort of virtual machines is there. Okay, so Paul's got his hand up. Let's pause there for questions about containers.
Yeah, I was just wondering, if I need to use Windows, and I'm a Mac user now, I kind of fell out with Windows a little while ago. Had enough of fixing other people's systems as well. But if I need to run something that only runs on Windows, it seems to me I've got 3 choices now. I can run Boot Camp, although I think that's being deprecated, isn't it? You can correct me on that. Or I can run Parallels on my Mac, or I can run a virtual machine, because I can't use a container because my native operating system is Mac now, and it's the M series chips. Is that right?
Do you know what? Can you hold that thought for a moment, because I've got a slide on this.
Okay.
And it's sometimes easier to talk when we've got a picture in front of us. Yeah, it's a really good point, and I did think about that for this presentation. Right, so once you've got these containers, the next problem you've got to solve is what's called orchestration. Commercially, it's very unusual to run one container, and that container contains all the separate parts of your applications. It's much more common to run several containers, maybe even over several physical hardware platforms, and those are networked together to combine to give your application. And now, one of the reasons I wanted to talk about image in the next meeting is because image is one of these examples which has multiple containers, and we can look at that in more detail at the next meeting. So we got this problem: how do we start multiple containers and connect them together? And that process is called orchestration. Docker has a solution for this. It's called Docker Compose, and you have a single configuration that defines how multiple containers start up. So you might have, container number 1 creates a web server, container number 2 contains a database server, and then you also give instructions how to network together these 2 containers. Oh, I've got an example there. Now, if you want to get really grown up on this orchestration, there is a tool from Google called Kubernetes. And I can talk forever on Kubernetes because that's one thing I worked commercially before I retired. Now, Kubernetes is like a grown-up Docker Compose, and it's designed for very large scale, very highly available applications running across multiple servers, running at high speeds. And Kubernetes takes the idea of containers and really turbocharges them. So we have a single configurations for multiple containers, and typical Kubernetes, they like to rename things. So containers are now called pods. You think of Peapod, it's another container type names. And Kubernetes deployments might be thousands of containers running together. Multiple physical servers, your hardware platforms, they call them nodes. And big thing is that Kubernetes will do auto scaling. So if you can imagine, the Amazon platform that's running all the shopping, at midnight, they might only be using, a few thousand of these pods. And then some people wake up at 8 a.m., they might have to automatically start up a new couple of thousand pods to absorb this new load that's just come on board. So Kubernetes is pretty good for elastic scaling. And it's also good at self-healing. So if one of your pods gets locked or crashes, Kubernetes will spot that and restart it. And one nice thing you can do with Kubernetes is what's called A/B testing. So again, if you've got these very large applications, let's talk about Amazon Shopping, and Amazon want to introduce a brand new website. What they can do is deploy that as an application on Kubernetes and use this A/B testing to say filter through initially only Amazon employees to this new application. And then a bit later, maybe 1% of customers to this new application, and then 50% of customers. It's really what you don't want to do with these big applications, to have a big switch over to a new version of an application, because if it goes wrong, 100% of your customers will be angry rather than 1%. And there's a little bit bigger. So Kubernetes is this big industrial strength way to manage containers. But all the principles that we talked about containers still applies. Right. So now we're going to talk about the question that Paul raised about how can you run containers on a desktop. So on my desktop here, and I'll show you in a minute, I've got a Mac. It's an M1 chipset, so it's an ARM-based CPU. It's Mac. So in theory, it cannot run Docker. But of course I can, right? So the way this works is, and I called it fake containers. So, so what you end up with is an operating system, and you run a virtual machine. So step one of running things like Docker on your desktop is to run a virtual machine, and that virtual machine is running Linux. And of course, once you've got Linux working on your desktop, then inside of the virtual machines, then you can start running your containers. So this is a pretty daft way to do things commercially on servers. It's not going to be very efficient. But if you're a software developer and want to start testing containers, it means you can test all sorts of things on your desktop now. It's not going to be the fastest way to do it, but you'll be able to run a Linux container, a Windows container, a Linux VM, a Windows VM, all sorts of combinations by combining these different technologies in this way. And of course, if you get tools like Docker or Podman, these have this virtual machine built into it. So you're not even aware that you're using it. But this is how it works under the cover. To run Docker on a non-Linux desktop, you have this extra virtual machine. Does that kind of come close to your question, Paul?
Yeah, mostly. In terms of context switching, do you just alt tab between these different things that are running? Does it treat them like jobs running in the background, or do you have to go through some process to say, well, I've finished editing my my document on MacOS, and I now need to check what's happening on this VM that I'm running?
So it's a good point. So virtual machines will often, or sometimes and sometimes not, have a display associated with them. So you can run virtual machines with no display, no graphical display. So you've just got like a TTY style interface to it, or you can run virtual machines with a full Windows desktop and such like. Containers will almost always have no display associated with them. There's no operating system there. There's no Windows desktop. There's no Linux desktop. It's running application. So they're textual only. And I'll show you in a minute. You'll typically run a container in the background. And so you've got multiple container run-ins. You can see which containers are running. You can look at the logs for each container. You can run an additional application, shell in a running container if you want to effectively log into it and so on. So containers tend to run in the background. There's no graphics attached with them, whereas virtual machines will appear as a window, and then you can use your desktop window manager to switch between them as you need to.
And can I dynamically change the processing power between them? So if I'm doing something that's just come up and just leave this thing running in the background, but allocate it low CPU time whilst I'm doing something else. Does the focus that you're on actually change the dynamic allocation of resources?
if you're talking about desktop implementations, the answer is typically no, you can't do it dynamically. You have to determine it when you start up your virtual machine or your container. If you're talking about, the professional installations on, Google or Azure or whatever, or AWS, then absolutely, they have all sorts of clever tools. And by the way, these server tools, the professional guys will not use Docker. They'll use alternative implementations of the Open Container Initiative standards, things like Containerd that do support these sorts of dynamic systems. One of the issues, most of us see containers and Docker as being the same thing. They're not. Docker is as one implementation of the Open Container standards. And one problem with Docker is what they've tried to do is one binary does multiple jobs. You can use Docker to create container images. You can use Docker to run container images and create containers. But if you're running this on the cloud servers, like Azure and so on, they really don't like this multiple use, because it means you're deploying Docker on this public server, which is open to attack, and on that server you've got all these development tools suddenly deployed. So
yeah,
the Azure and so on will not use Docker. They'll use things like Containerd or Podman, which has got a single use, and that is to run containers. You can't use that binary, and they are much more secure. They've got different permissions in them and so on. You can't run root applications inside your container and all sorts of things like that. A bit more grown up, a bit more professional.
Yeah, in a way, is having different users which can be logged in at the same time, but obviously only one can use the box at any one time, is having different users in Windows or Mac OS similar to a sort of containerization, because each user can only see their own working space, as it were.
Yeah, when a container starts, everything that's running inside that container is private to that container.
Yeah.
And you can't really log into a container, but what you can do with a container, you can run an additional binary such as a shell, and then get access to it. So it's a little bit, it's not quite a virtual machine. You can't really log into it, but
you can move resources in and out, which you can only do between different users on a box by having a shared area.
Yeah. I mean, things like Kubernetes systems, like Red Hat's Kubernetes is called OpenShift. Their security arrangements is absolutely bonkers. Each time you start a container, it runs as a random user ID. Any kind of privilege escalation, like sniffing the network, is absolutely banned, and all sorts of stuff. So these grown-up environments for big applications really are locked down. And some of the stuff you can do on your desktop in Docker and your desktop virtual machines is you just can't do on the big servers. Pete,
I think it's important to understand the difference between a VM and a container. Okay, a container is really just an application, and what Peter was describing, where you could run a shell, is really a kludge that's mostly available in Docker. But at the end of the day, the whole intent of a container is to containerize an application. And what that means is that you bundle in all its dependency libraries. So what you can do is you can issue your application and it depends on nothing else in the system, which makes it very easy to sort of manage deployments. And as a user, it makes life very simple for you, because you don't have to make sure you've got the right Windows libraries and all that rubbish. So for example, on Linux, Ubuntu, they now give preference to issuing applications as snaps. And snaps are they're basically containers. So it's the application plus all the libraries that application depends on. So you don't need to, there's no real installation concern you have to go through, right? And that was really the same goal for Docker. The idea is you could download a whole development environment, which was as a Docker image, and you don't have to worry about configuring your system or setting it up. You just run it. And if there are updates, they're made by the developer and you just wouldn't really know about it. If you want to do anything more than just run an application, if you want to tweak with resources or play with what IO devices it can get at, you really should be looking at a VM, because the VM is basically an operating system with a bit of isolation. That's the difference.
Thanks, David. All right, got some hands up. Peter.
Thank you again. It's really, really interesting. I'm trying to get my mind around what's fixed and not fixed. I like to have a sort of bottom line on these things. The application language we use in these systems, how much variability is there on the application language we use? And obviously the libraries that use the word binary. Now, the word binary to me has an implication of a set of instructions, sometimes the machine level, or sometimes they're going to be interpreted instruction like in Python. So where are things fixed and not fixed in this model, please, Peter?
Yeah, so you get a lot of different sort of common types of containers. In the IBM video, they mentioned JavaScript containers. And the way you would build one of those containers, you'd take a standard container image with the JavaScript libraries and then add a new layer, which is your application. So when your JavaScript program is running inside your container, it has any JavaScript libraries or really anything else it requires to support it. And also you can have Java containers, you know, and a standard Java containers will have the Java runtime as a binary, and then you'll have your Java jar files and whatever else you need into it. And, you know, you can build C programs and run those in container, whatever you like, really. But very common usage is these common, I don't know what to call them, these tool chains really for common applications like JavaScript, Java. You know, these days you have a Rust and so on and so forth. So they are really quite flexible.
So basically, where does the actual machine instructions reside? Is it in the container engine that you go into actual machine instructions at that point?
Yeah, so the container will be running a binary of some sort, and that might be Java runtime or, you know, your program written in C. And when the container is stepping through the instruction sets, they are all getting executed in the host kernel. This
Can
the
application itself contain machine instructions, or is
yes.
that's just it can?
Yep, that's all going to be executed down here. All right, the kernel here has got support of this is a bad sorry this is you know, we should have gone back a bit really, but the container engine's giving you really very fast access to the underlying Linux kernel. Remember, this is Linux compiled applications running in a Linux container running on a Linux kernel, and it's the Linux host kernel that's supporting your application directly.
Okay.
So we've not got this step where we've got in a virtual machine, we've got another operating system kernel, we've got that extra layer. We don't have that extra layer in containers. What containers is about is an isolated environment, but all the code and the call outs to the library functions are really executed directly in the host kernel.
So to what extent does it affect the compiler which you're using to generate the application?
So what you typically do, if you are a software developer, you build up in your build system a mechanism where you can build your application and test it natively, locally, perhaps.
Yep.
And then the build system would also generate a container image.
Okay.
That container image, inside that container image, you put the binary you've just compiled, and you put any libraries it requires, and then you push that container image to a server somewhere so that someone else can download it and run it.
Got it. Okay, thanks for your help, Peter. Thank you very much indeed. Thank you.
Paul.
Yeah, I was just wondering about the other resources on a box. Assuming you haven't jailbroken it and booted straight into it, if, for instance, access to your camera, your microphone, your position and things like that, are they mediated by your native operating system, or are they mediated by either the VM or the container engine that you're running? And can you make exceptions?
Yes. So remember, this is containers running on Linux. So the way you actually do it with Linux, devices such as cameras and GPUs and so on appear on the file system in the /dev file system structure. So what you do with a container is you allow a container access to a particular /dev/ something, whether it be a camera, whether it be a software-defined radio, whether it be a GPU, and so on. So you have to specifically grant a container access when you start it up.
And on a VM?
On a VM, you would configure the VM to access particular resources. Typically, if it's a camera, you probably grant your VM access to USB bus.
Right. Okay. And you mediate that when you install the VM, and that mediates that with your background operating system.
No, sorry. It depends on what you mean by mediate. What do you mean by mediate, Paul?
Well, I lock my a lot of my stuff down for privacy reasons using macOS. But if I'm going to run something else, I want to make sure of two things. One, that doesn't get violated, or two, I've got fine control of how I allow that to be used by other systems. Okay,
so well, a couple of points. So I'm running Linux. I don't know what the case would be for macOS. So on Linux, the Zoom application I'm running now is a container, and it's accessing my audio and my camera. Okay, and if I share a window, it's obviously accessing my desktop as well. So it gives you a feel for how easy, if you like, it is for the container to be given access to various resources, although that's under your control. You can turn them on or off. If you run a VM, again on Linux, I run KVM. Basically what happens is you have to tell the VM what USB device to allow the VM to access, and that's on a per VM basis. So for example, if your my webcam is USB, therefore the only way an application running in a VM can access it is if I go to the VM's menu and enable that USB device for that VM. But only that, no other VM, no other application can then access that USB device.
Right. So yeah. Okay.
Now that's going to be true for any USB device. So if I plug in a USB disk, it's the same again. And as Peter mentioned, any device really acts as in a fairly uniform way through the Unix file system.
Right. And is it normally off by default, or does it depend on which particular thing you decide to put on?
Yeah, it's off by default. You have to enable it. I mean, was a bane of my life when I'm developing stuff, because I always forgot to allow the USB device connection through.
Yeah. Okay. Thanks.
Okay, so I thought I would skip on to some related topics. We've talked about virtual machines, talked about containers, but actually it's not the only way to do this stuff. There are other options, and it gets a bit mind-boggling after a while. So, first question is, what about applications written for a different CPU? So I've got a Mac, there's an M1 processor with an ARM chipset. I can run Intel binaries on it. And how on earth is that going to run at anywhere near native speeds? I mean, it's just the mind boggles sometimes, but you can do it, right? So first thing is, in virtual machines, it's possible to emulate a full CPU, but this can be really slow. So one thing I used to do, for example, I had a little disk NAS box which had some I don't know, some weird CPU on it, and it was possible to emulate that on my desktop and load the disk image on my NAS on it and fired up my NAS on my desktop, emulated a CPU. So this stuff is possible. You can emulate a Intel CPU on an ARM chipset. You can emulate an ARM chipset on a Intel CPU and so on and so forth. And this emulation, though, can be slow. All right. But here's a trick. There is this thing now called machine instructions translations. So the way this works is you take, if you're trying to run some ARM code on your Linux desktop, these translations will take this ARM code, they'll convert it to some internal representations, and then generate native Intel code. And that native Intel code can then run at full speed on your Intel hardware. How do they do that? Mind boggles. So a couple of implementations of this. Very common one, which probably very few people have heard of, is a thing called QEMU. I'm never sure how to pronounce it. This has been around for years and years and years, and it can do virtual machines. It can do full emulations of hardware, including instruction sets, and it can do this translations in a subset of cases. And one of the big recent ones actually is Rosetta 2, which I've got on my Mac. And this actually cheats a little bit. So Rosetta 2 is a Mac-only application, and it allows you to run Intel applications on your ARM desktop at full native speed. And it does this partly by instruction code translations. So it actually converts the Intel code to ARM code, but it also makes use of custom Apple-developed hardware on the ARM chipset. So there's a bit of a software-hardware combination, this. But actually, it's frightening how it can do it. And tools like Rosetta and QEMU are very often bundled into a hypervisor or a container image, so you're not even aware that the stuff is going on. Now, there's also other approaches, further approaches. So if all you're trying to do is to run an application probably designed for a different operating system, you don't always have to run run a virtual machine or a container. There's some other options available to you. So there is, if you're not aware, a development platform really on Windows called .NET, and enables programs to build up Windows applications. And the .NET libraries include, sort of windowing widgets and buttons and sliders and all these sorts of stuff. But it turns out .NET is actually cross-platform. So you can run .NET on Linux. And the .NET implementation is called Mono. So if you're in Linux, Mono provides a .NET runtime, and you can actually do something like this: run Mono and then a Windows binary. And this Mono provides all the .NET cores that application requires. So there's no emulation going on here. The .exe is run natively on your operating system, and when your application is running and it runs on a .NET core, Mono then provides a .NET core rather than Windows, the native Windows. The biggest downside with Mono is that vast majorities of Windows applications that claim they're .NET also use a whole bunch of other APIs, and then this trick doesn't work then. But there's another one which is worth mentioning, and that's the Wine project. And this has been going on for years and years and years. And it stands for Wine is not an emulator. And it's a way to run Windows applications on Linux. That's a reason for it to live in. And similar to Mono, it provides Windows 32 and other APIs. It completely, basically re-implemented all the Windows libraries, all their APIs in Linux, a complete re-implementation. So again, the application is run natively, but any Windows calls to, draw boxes or whatever it might be, is then directed to the Wine implementation of those libraries. And, like Mono, you can just run Wine and then your Windows applications. And Wine is these days very grown up, Although it's always in catch up with, you know, the Microsoft API changes, there is a commercial organization that supports it now, and it's called Crossover from Codeweavers. And Crossover, you can download it, you can run Microsoft Office, you can run Microsoft Flight Simulator on Linux, and so on and so forth. And the Crossover Office is really quite mature now, and they offer commercial support for us. So the Wine project is kind of quite interesting. It's gone from like a hacker's way to run Windows app on Linux to, you know, a full commercial ecosystem. And just last week, I noticed that Microsoft has donated the Mono to Wine project. So both of these have worked. And yes, you can run Mono inside Wine and so on. It gets a bit carried away. So I just wanted to mention that, you know, virtual machines and containers is not the only way to run applications, which is, you know, your desktop's not destined for. And certainly when I used to use Linux, when I, you know, threw Windows out the window, literally, I use Wine and Crossover a lot. And of course, these days, although the purpose of virtual machines containers was originally to save on resources, it's got a lot of use on the desktop now, but this is like a secondary use, really. So if you're running a Mac and you've got this annoying Windows app that you absolutely must run, then, you know, you can run it on your desktop under a virtual machine. If you're a developer, you can do when the next version of your operating system comes up and you're saying, oh God, will it work with this weird application I've got? You can fire up a virtual machine, load this new version of the operating system on it, maybe Windows 23 or something, try your application out before actually doing a big install on your desktop. And if you're a developer, it's really good for developers, because if you're doing cross-platform development, you can choose your favorite desktop, whether it be Windows, Macs, or whatever, do a development first, and then you can test on all the different operating systems, all different containers on your single desktop. Right. I'm just about done for talking. What I thought I'd do is to have a quick look before we wrap up of what it actually looks like, if that's good for you. So what I'm going to do is to share my desktop again. This time I'll share the whole desktop. Right, hopefully you can see this. Hopefully you can see this. So here I've got a Mac application called UTM. And there's lots of different virtual machines hypervisors you can get. I've picked UTM. And we can, you know, I've got a virtual machine ready to have a look at its configuration, if you like. Very little to look at, to be honest. It's got some various, you know, display settings, network settings, a whole bunch of systems, you know, memory allocations and such like. I tend to leave it to default. And when you run this application, this virtual machine, you'll see it. Okay, so it's running a complete bootable operating system. You can see all the normal startup messages. This is though you've plugged in, you know, got a real physical hardware. And you can see it's going to take some time for all the various kernel services to start up and so on. And eventually, you know, we've started up our desktop. We've got, you know, a virtual machine running in a window, and we can log in. And you'll notice here that my mouse, I've got it on my desktop here, if you can see it, and I just move it into there. And now this is controlling the mouse in the virtual machine. This is one of these features of there's tools that you install to give this seamless integration between your desktop and the virtual machine. And heck, you know, I can drag the virtual machine, and if I've set it up right, you know, I can resize the screen and so on. So there's some additional tools I've got installed that makes the desktop integration a bit smoother. But you'll see it took a little bit of time to start up. What I've also got here is Docker. Now I've got the boring somewhere graphical Docker running, but I always prefer the command line. So Docker is a command, gives you a whole bunch of stuff you can do. So the way you run Docker commands is, I'll just show you, I'm just opening up my cheat sheet here. Docker, run, you're going to run a container, hello world. This, if you look at any container course, this is what you run first. Docker, run, hello world. Now, what's that saying is, please start a container with a container image called hello world. And if I run this, you'll see, it's quite chatty, that this container image wasn't found locally. So Docker has gone ahead and downloaded it for me, and then it's run it. And this is what this container image does. It just says hello, and that application exits. And that's it. So if we run it again, it'll be instant because the container image has already been downloaded and it started up. So there's no operating system started up. We run this application immediately. Now, if we're going to do something a bit more sort of like non-trivial, I'll just cut and paste something here, which I've prepared earlier. So Progress is a relational database. And if you're going to install Progress, normally you'd have to, get hold of the installation, make sure you've got all the libraries set up on your desktop, install it, create the basic tables and so on. But hey, Docker, you can do it in one command. So I'll do this. Again, it's not found the container image locally. Now notice here, we've got several downloads happening in parallel. This particular container image has got several layers, and you can download these layers in parallel. If I just scroll back up again. So I've asked Docker to run this container called Postgres. It's downloaded the image and it's started the container. And these messages here is just the messages coming from when the database is starting up. So again, no operating system to start up, almost like instant. In fact, if I stop it, and if I run it again, the application starts up immediately with containers. And this is the big advantage with containers, just the startup speed. And you imagine you're doing, using a container, a bigger container system like, Kubernetes. You've got thousands of containers. You can start and stop them really whenever you like on demand. You can route traffic through different containers. You can really get quite hardware. So I'm not going to go too much into it. Perhaps I'll just do a different thing as it comes up. One thing you can run with is to run the container in the background. So if I run that again, I've got the -D option to Docker, which means run in detached state. So if I don't do that, then I can just hit Control-C and stop the application. But if I run it detached, then all we do is run it in the background, and then we can see Docker, PS, we can see it actually running in the background. And if we can do Docker logs, we can give the name of the container, and we can view the logs and so on. And of course, you can do these graphical applications to do exactly the same sorts of stuff. So that was the end of the demo. I just wanted to give a feel for it. Virtual machines and containers all running on your desktop. So we've pretty much consumed our time. Are there any more questions? Have we finished? Stop sharing, that would be a good idea.
Quick question. Android on Windows?
Yes, you can do it. You can get a virtual machine to run Android operating system. Don't ask me the names, but I know you can do it.
Okay, thank you.
And you can run games and all sorts,
Android on Linux?
Yes.
Okay, good. Thank you. I'll find
I mean,
that.
you will find a virtual machine somewhere, and I bet most of them will be based on this QEMU open source application.
Yeah, so QEMU, however you want to describe it, it's well established on Linux, and you can run both 32 and 64-bit ARM machines, so you can emulate almost any phone if you want to run. So you can emulate the Android running on your choice of tablet or phone architecture.
Yeah.
Thank you. Thank you.
Paul.
Yeah, I'm just wondering if you want to run something fairly heavyweight that doesn't run native, like a copy of Excel or a flight sim or one of the more hungry for resources games that only runs on Windows, what would be the recommended way to do it? And does the new M series emulation that's built in, or the translator, I forget what it's called, does that do it for you, or do you end up having to run a VM and put Windows on there?
There'll be more than one answer. So
do the Linux one.
The first one I would say is not run Excel, to be honest. I would choose a spreadsheet. To me, if you want to run Excel, the problem is I want to run a spreadsheet. And then, okay, so you've got Google Sheets, you've got LibreOffice, you've got Apple Numbers, you've got lots of other implementations. So I think you'd have to come up with a good reason why you specifically wanted to run Excel.
It's built-in macros and things like that, and stuff that you get from other people that you need to be able to run in that kind of environment.
Yeah. So of course,
get a copy of LibreOffice, run LibreCalc, import the Excel spreadsheet, and see if it works for you. Because it's all free, so you're not having.
Well, you can do it on macOS, but I have had problems with things not working because it will only run in the native Windows environment.
So you can.
No, you don't run Excel. You run LibreCalc and import the Excel worksheet.
Yeah, well, I mean, I've done the sort of same using macOS, imported into Numbers, but some of the fonts aren't there and some of the macros don't run properly.
So coming back to your question, so so I started off with, if you could use a native alternative and do so, would be my starting point. If you were running Intel Linux, then Wine would definitely be your answer, because Wine fully supports Excel and Office and Word and such like. I don't know the status of Wine on ARM. Who knows? It might work. But I suspect you will be into running a virtual machine, running Windows, and then running Excel in your Windows. Now, I used to run Parallels back in the day. I don't have the need for virtual machines anymore. I do everything natively. But I remember Parallels had some nice features where the actual Windows inside the Windows operating system, you could actually have them as separate windows on your Mac desktop. So it kind of looks almost like fairly well integrated. You've got these tools that run inside the virtual machines that allows you to extract any running window and put it on your Mac desktop. So you don't have to have all the Windows taskbars and such like. You can hide all that nonsense.
Yeah, I haven't kept up with whether Parallels is still an option after they went to the M series chips, but that was what a lot of people were recommending, or do rather than doing boot camp, which means because with Parallels you can just dip in and out of whatever you want to do, rather than reboot each time.
Yeah, and of course you might find Excel is available natively at a cost.
Yeah, okay. And what about the heavier stuff like the flight sims and the gaming? What are people doing on Macs these days?
So,
are they just
Mac
with the Mac catalog?
Yeah, so things like Microsoft Flight Simulator will work under Wine on Linux.
Okay.
Linux is quite well supported on these sorts of things by Wine.
Actually, you can go one better than Wine. So what when you ran it on PC, did you run it with Steam?
It's years ago. I'm resurrecting some stuff at the moment because the problem I'm having, is that some of the stuff that I want to run is not really in the App Store for. It's not made. Not everybody's ported to macOS.
Oh, they won't. So for Linux gaming, you want to use Steam. Steam.
Yeah, Steam. I was looking.
They've spent a lot of money on developing Wine specifically for game, and on Steam it's called Proton. And basically, when a new game comes out, they aim to get Proton upgraded as quickly as they can to support the game. So when you go on, if you're running on a Linux platform and you run Steam, quite often now you'll find the game is available as Linux native, but if it isn't, you can run the Proton environment as like a compatibility layer. And quite often the game will run without any problems at all. I'm not saying there aren't some games that are problematic, but I haven't found any yet.
Right. Okay. Because the other thing I'm thinking of doing, I think when the next version comes out, which I think will be M4, is to repurpose my old Intel Mac Mini and put Windows on that, because I've also got quite a bit of Open University software that I'd like to be able to run again, because I never had time to finish the courses at the time with other things going on and being in full-time work at the time. But they only run on Windows in a Windows environment, and I don't have a Windows box anymore. So I'm thinking that might be another way to do it, is just to repurpose that machine and put a version of Windows on it and run everything from that.
I tell you another option that could be available to you, depending on stuff, is that the Mac M1s, M2s, M3s can actually run iPad apps now. And you find that games and such like tend to be available on iPads before Macs. So you can just go to the App Store, press a tab to say, find iPad apps and install iPad apps. Because iPads, after all, got an ARM chip in them. So, you can run those.
I know the problem we had with the OU is that whilst most of the lecturers nowadays in any science profession tend to use Macs, they only supported Windows because that's what most of the students had. And so some of the modeling stuff that I need to be able to run again will only run in a Windows environment.
I'm a bit surprised you say that, because, when I've been to universities recently, everyone seems to have MacBooks.
Yeah, it may have changed recently. The thing is, Peter, I've got old software I'd like to reuse.
Oh yeah,
as part of the courseware,
I get the requirement.
And that's why I was thinking, what's the easiest, quickest, pain-free way to do this?
Yeah. The only thing I would say is, if you're doing virtual machines, there are several tools, things like Puppet, that allows you to build the virtual machines in a consistent way. So, as a developer, I'd always want to be able to rebuild, installing a operating system inside a virtual machine and all the dependencies and such like is very easy to kind of miss out some steps. So if you record everything that you've done as a script, then you can blow away your virtual machine, and then a couple of years' time you can rerun your script, and that'll recreate your virtual machine with all the dependencies into it, ready to go. So the problem I always find in virtual machines is it's all manual. Someone says, I've got a virtual machine which I've created to do this. Well, how did you create it? I don't know. Here's the image. 200 gigabytes of the stuff you have to download. Ray.
Yeah, right. Very interesting talk. Thank you very much for that. Today's difficult question. I don't suppose there are any ready-made containers or whatever out there to emulate Acorn's RISC OS.
I bet you could find it.
Okay, we don't know the instant answer. I've got to go searching.
Well, QEMU, I bet QEMU will support RISC-OS.
Really?
Yeah, have a look at it. And there are some good QEMUs, sort of like command line tools. So let's have a look. Since you ask it.
The short answer is yes.
Oh, you've already looked it up. You beat me to it.
So if you go to riscosopen.org, which is that's probably the best place to look for practical advice.
Right. Okay.
QEMU will emulate two architectures. One is the Intel, and the other is ARM.
Oh no,
And that includes the old ARM that Acorn used to use on the
The 32,
Archimedes.
well, the 32-bit, but I think now whether it's
Yeah.
doing it natively or they're using a HAL of some sort, a hardware abstraction layer, I'm not sure. I haven't looked at that. But I've
Right.
definitely seen RISC-OS being run. Oh, what was it on? I'm sure I've seen it run on QEMU somewhere.
Okay, with the full graphical mode, not just command line stuff.
Well, that's what I'm trying to deconfuse my brain about. I know
Yeah.
I've seen it on FPGAs, but I don't know if I've seen it.
FPGA. Okay.
Oh, you can emulate anything on FPGA.
Well, yeah, if somebody's got the effort. Yeah. Yeah. Okay. Thank you.
yeah, definitely explore it. I'm just looking up the docs as you say, but here we go. ARM MIPS 2, MIPS 3, loads of ARM stuff, Banana Pi, Zen, MIPS,
Which version of RISC-OS?
RPC.
It's RISC OS 4 or RISC OS 5, one of those either ones.
So yeah, there's a comment here in that forum I mentioned, riscopen.org, where they're talking about running RISC-OS Mark 5.
Oh, okay.
Version, where we got? Oh, Mark 2,
RISC.
Mark 4.02.
Yes. Yeah. Yeah.
Yeah, I mean, yeah, you'd have to do a little bit of archaeology.
Okay. Right.
Forum.
Spark,
Thank you.
mainframes. I'm just looking through the docs. Actually, loads of hardware. I mean, it's different. Each hardware platform is supported to a different level. So sometimes you can do a full system. Sometimes you just need to run a given binary, which is compiled for that process. You just run it from the command line.
Yeah. Well, mainly one of us, the modern software.
Okay. Any other questions or comments or thoughts before we hang up?
It seems to me that VM is quite useful for other things too. I can remember in the distant past programming in C, a little bit of C++, and when you get things wrong with pointers and things, you can end up writing all over your memory and things like that, and causing all sorts of problems on your box. And it seems to me that, particularly if you're learning a new language, running it in a VM is quite a good way to do it, because you protect the rest of your system.
Yes.
Yeah, particularly if it's Windows. I mean, Windows has all sorts of security issues. You can splatter over other processes and whatnot. All right. So I'll say again, so next month, I thought we'd talk about this image application, because it does use containers under the covers. It uses AI and all sorts of. So I think there's quite a few things that we can explore there. It'll be interesting, as well as it's kind of interesting application to play with. All right, if there's no other points, let's draw it today to a close, and I'll see you all next month. Ta-da.
Thank you very much, Peter. All the time and effort, but it's very
No
kind
problem.
of you. Thank you very much indeed. Really good.
Yeah, thanks very much, Peter. Really helpful.
Thanks, Peter. Yeah, great.
Yeah. Thanks,
I'm
Peter.
a bit confused now. Anyway, it's great. Thank you very much
Have a
indeed.
look
Thanks a lot.
inside my mind, blimey.
All right. See you next month.